And we're back with the chain rule, the mother of all derivative rules. And we did guess and check for f of x equals cosine of 2x. And maybe you guessed it right, maybe you didn't. Either way, it's not important. The important thing is, when it comes to the chain rule, is we need to take the derivative of whatever function we're substituting into the function, as well as the function that we substitute into. That's the big idea here. Or expressed slightly differently, but with the same idea, we want to do that first activity we did today, where we identified the functions. And then after we identified the functions, we take those derivatives. That's what the outside prime and inside prime are. So the outside function we said was cosine of x. The inside function was 2x. The derivative of cosine is negative sine of x. The derivative of 2x is 2. That part isn't new. What's going to be new and different is how do we know how to put them together? And we're not really going to prove that this is the case, but for the chain rule, when we take the derivative of both parts, and that's the most important piece. And then the only thing we have to do from there is just remember how they fit together. And they fit together with multiplication. So in this particular case, we could say the opposite of sine of 2x times 2. Or if you wanted to say the opposite of 2 sine of 2x, also fine. Either way, it gets us to the correct derivative, which again, we verified by looking at the graph. So the blue is covered up perfectly by the red. So that's how we verified that, like we've done a few derivatives. So the order there does not matter, but there is one particularly pesky detail that we will get into more as we do a few of these with the chain rule. So what are we going to understand the chain rule to be? That was a little bit further than I thought. Sorry. I'll get this reorganized. Here we go. So we'll start out by defining the chain rule the same way we started out identifying composition in the beginning. But this time we'll be a little bit more specific about it. So we'll just say h of x. So h of x is f of g of x, and f of g of x is the same thing as before. So h prime of x, the derivative of h of x, is going to be f prime of g of x times g prime of x. So we will call that the chain rule. There are many correct ways, notationally speaking, to write the chain rule. We're going to use this one because that's how we started out with the pre-calculus task of deconstructing a composed function. So we're going to keep the same notation here, just to make it look consistent. So if we look, this matches exactly what we did when we took the cosine of 2x. So we identified the function that gets substituted into the other function. That was 2x. We took the derivative of cosine, that's negative sine. We took the derivative of 2x, and then we said that we have f prime of 2x, so negative sine of 2x times the derivative of 2x, which is 2. So if we're thinking about the chain rule, notice how, and this is important, we have the derivatives of both the inside and outside function. There's f prime and there's g prime. There's really only two pesky details to keep track of after that. One of them is that we multiply. That's not the pesky detail. The truly pesky detail is this part. Notice how g of x, just like it's here inside of f, nestled nice and safe inside, snug as a bug in a rug, it's nestled nice and safe inside of f prime. So that part doesn't change, the g of x. It stays inside of f, whether it's f prime or f. So again, chain rule, using the same notation that we introduced this with, H prime is going to be F prime of G times G prime. Okie dokie. So we have studied now almost all of the basic derivative shortcuts and the some not so basic, as well as the mother of all derivative rules, the chain rule. What I need you to do is shift your thinking when it comes to taking the derivative, now that we have all these things. And there will eventually be a fourth thing on this list. So when you start thinking to yourself, okay, this problem is saying take the derivative. What am I going to do? You're going to think about these three thoughts. So we're thinking about these three things at the same time. And yes, it's hard to do. There's no particular order you need to engage with them in. I can tell you what I typically do. I always think about the chain rule first, and then I think about the product and quotient rule, and then I think about basic shortcuts. But there are people who have the consideration in a different order that are equally successful as I am when it comes to taking derivatives. And again, taking a derivative means performing the derivative operation. So you're reading a problem and you're like, you know what I need? I need the instantaneous rate of change. And I have a formula. Okay, I should be thinking about these three things. Or you're looking at a function and you're like, I need to write the equation of a tangent line. Okay, I should be thinking about these three things. And I think that that can be a really powerful way to organize your thinking, because it helps you in those situations when you don't know what to do. You don't need advanced strategies for something that you've already figured out. I don't think that's earth-shattering for me to drop that tidbit of knowledge on you. You don't need help when you don't need help. So the question is, what do you do when you need help? And you rely on really strong habits of mind. So I'm saying when it comes to derivatives, these three things, and there will be eventually a fourth thing that you always think about anytime you take a derivative. Speaking of taking a derivative, let's do a few. You remember this guy, don't you? Sure you do. Now, these examples are going to start out feeling manageable. I don't say easy, because the chain rule is not easy. The chain rule is one of the more difficult things in calculus. But manageable. And the reason why it's manageable is because I need you to go back in time while you're writing this down and think about how you've already seen this problem, and we have already considered that the chain rule applies here because I have a function inside a function. So we've already done all of that thinking. We don't have to redo it. And when you've got a brand new function you've never seen before, you have to re-engage in all of that. And that creates some processing load that makes it more challenging. So I'm not going to write F and G like I did before, although you're welcome to do that, because it can get confusing if the function is called F or G, and I don't want you to confuse yourself when you're trying to do this. So we already know we're using the chain rule because we already know that this is the composition of some functions. So I'm just going to, instead of F and G, just say inside and outside. So if you recall, the way we did it was we said G was going inside of F. So the way we organized it before, pay no attention to letter B, that's coming later. We've already identified that x squared minus 3 is being substituted into the function sine of x, right? We've already identified that. Okay, so if there's one thing I hope you know about the chain rule, is that it is applied to the composition of functions. If there's a second thing I hope you know about the chain rule, it's that you need the derivative of both the inside function, that's the function that the other function's evaluated at, and the function outside. So as I abbreviated inside and outside, I and O, I prime and O prime. So it's not going to shock you to write down the derivative of x squared minus 3 is 2x minus 0, and it's not going to shock you to say that the derivative of sine of x is cosine of x. When we get to putting everything together, we have those two peculiarities. So the first one is we're multiplying. What are we multiplying together? We're multiplying these derivatives. The second peculiarity is we're not going to have a cosine of x in our answer. We're going to have a cosine of x squared minus 3. One way you can think about this is when it comes to evaluating. So if you think about the composition of a function, like let's say you have f of g, and you're evaluating at x equals 5. Well, the first thing you do is you'd evaluate the inside function at 5, and then you do the outside function to it. So that evaluation process is part of the function statement. So we want to continue to keep the same the x squared minus 3, just like it's pictured here. And I know it's weird, but this x right here and this x right here is actually a 2x. That's actually a 2x. So that's always a 2x. And again, the reason why that is because of how composition works. You take whatever value you have for x, you substitute it in to the inside function. You do all of that, and then you take whatever the remaining operations are. That's not brand new information. But the peculiarities of fitting it together with multiplication and preserving that x squared minus 3 everywhere, those are difficult to manage. So to be brief about the calculus that's happening, the x squared minus 3 is the same calculation each time, but what's changing, like what you're taking the derivative of, is the x squared minus 3 operation and the sign operation, and we multiply those together. Okay, let's move on here to another problem we've already looked at. And that was this function. So this function I've declared to be the function g of x. And a while ago we said that we're substituting the opposite of cosine of x into 7e to the power of x. That's what we decided. So this is not actually how the chain rule would work if you're practicing on your own. The reason why is because we've already determined A, that the chain rule applies, and B, that we've got this kind of inside-outside action. So when it comes to the chain rule, I want you to keep thinking about, I need the derivative of the inside function, so the function that goes in, so like f of g, I need the derivative of g. I need the derivative of the outside function, so that's like the function that the function goes into, that's f. Or I called them I and O for inner and outer, so we need those derivatives. These derivatives are not going to come as much of a surprise. We're used to this, maybe. We do want to be careful here because these are slightly different. We have the opposite of cosine of x. So when you take the derivative of the opposite of cosine of x, you have the opposite of the derivative of cosine of x, which is the opposite of sine of x. And when you take the derivative of 7e to the x, remember that that is the constant multiple 7 times the function e to the x. Derivative of e to the x is e to the x. So you have 7 times e to the x. Or when you put them together, so before you put pen or pencil to paper or fingers to keyboard or however it is you're writing this down, I just want you to pause here and think about how does this fit together? That way you can assess in this moment if you know what's going on. Did you come up with that? I hope so. So notice something very important. Oops, that is the wrong color. Sorry. Notice something very important. That opposite of cosine of x is the same as the original opposite of cosine of x. So as you're going through this, remember that the outside function, we have x there, but x is just like a placeholder. That x is actually the opposite of cosine of x. It's very difficult to get used to. You could, of course, if you were feeling it, change the order here. You could have 7 sine of x times e to the power of the opposite of cosine of x. That's also fine. About the only big mistake you can make here in writing is you want to be really mindful that this opposite of cosine of x is the exponent of base e. And when you take the derivative of that, you're multiplying sine of x, not as part of the exponent. So in terms of order of operations, you do cosine of x, opposite e to that power, multiply by 7, and multiply by sine. So be very careful with that. Okay, let's take a look at our third one. Again, we've already done the heavy legwork on. What I would like you to bring to the table this time, other than a positive attitude, is some derivatives. So we've already taken the time to identify that we are in fact using, there we go, a function, sorry, not a function. These are all functions. We are using the chain rule. How did we know that? Well, we identified that we have the composition of functions. We have the natural log of x plus cotangent of x inside of x to the fourth. So here's where I'd like you to be the captain of your own ship of the line. I'd like you to write down what those derivatives are. So what do you have for a derivative of x to the fourth and derivative of the natural log of x plus the cotangent of x? You have the derivatives like so. Yes, no? For x to the third, 1 over x plus the opposite of cosecant squared of x. Remember, cosecant squared of x is cosecant of x and then squared, so you could write it that way too. That's actually much more helpful in terms of doing the chain rule, as we will find out later. Not just yet, but a little bit later. Okay. So I'm going to ask you to step up a little bit. I'm going to ask you to step up and try to do a little bit more with the chain rule. So we're talking about h prime of x. I want you to think about what this looks like if you were to put this together in the chain rule. So you don't have to commit to writing this down, but you can. So go ahead and give it a try. And if you're not comfortable giving it a try, at least engage in that really honest conversation with yourself about what you'd do here if you had to, because one day you're going to have to. Okay. So let's check in. Were you thinking, or did you write 4 times the quantity of the natural log of x plus the cotangent of x raised up to the third power times the quantity, notice how I have parentheses around this entire thing, 1 over x minus cosecant squared of x. It's really important to get those parentheses in the right spot. A common thing I see is the following. Now, I know what you tried to write when you did this. However, you have written math that is not correct. Why is it not correct? Because these two terms are part of the derivative of the natural log of x plus the cotangent of x. And what you've written is you're going to do this times just this. It's got to be times both of these, and preferably after doing each operation. Now, something else that I want you to keep close track of as you're working through your chain rule practice is this. Notice how those are the same. It's x to the fourth, but not x, natural log of x plus cotangent of x. And then 4, x to the third, but not x, the natural log of x plus the cotangent of x. I know we're doing some very quick and underestimatingly difficult math here, but you want to make sure you're taking time to build these connections for yourself, because those connections are what are going to make you feel confident when you're doing this on your own, and confident that you are coming up with maybe not the correct answer, a reasonable facsimile thereof. Okay, so I have for you a brand new practice problem. We have never thought about this, but as this is brand new and your first time, I will give you a hint. The hint is you should use the chain rule here. So that is your hint. I will give you some minutes to practice. So your big hint was to use the chain rule. Remember that that's not always going to be your hint. What you need to do anytime you're about to take a derivative, as yes, I'm going backwards, is you need to think about these three things. You need to think about basic shortcuts. Am I going to use the product rule? Am I going to use the quotient rule? Am I going to use the chain rule? And not just those things, but just a general idea of how they work. So that's the normal way you're going to take the derivative. You've been spoiled here for these first four into thinking that we're always going to use the chain rule and it's always going to be set up ahead of time. And while you're going to always think about using the chain rule, you're not always going to use the chain rule. So we're using the chain rule, which means we need to identify an inside function. So the function that gets substituted into the other function, that's x plus 5. And the function that we substitute into is 4 times x to the power of 6. And then we need to take those derivatives. So the derivative of 4 times x to the power of 6 is 4 times the derivative of x to the power of 6, which is 6x to the power of 5. Then the derivative of x plus 5 is 1 plus 0. And now for the payoff pitch. Did you put it together correctly? Did you put it back together as 24 times the quantity of x plus 5 to the 5th? I hope so. Because if you did, you exceeded my expectations. Well done. We are going to look at a couple of more examples here, but something that I would like to highlight is letter D can be done without using the chain rule in 2 respects. One of them we will get to later, but the one that I'll mention now is we could algebraically multiply x plus 5 times itself 6 times and then distribute 4 everywhere. We could do that, and then we'd have power functions to take the derivatives of. So we could do that here. We don't need the chain rule. There's another reason why we didn't actually need the chain rule here, but more on that later. Instead, I'd like to draw your focus attention to z, or if you're of the European persuasion, z of x. So that's cosine of x divided by 1 minus sine of x. No hints this time. Give it a try. Before I start sharing with you correct work here to explain what the derivative is, I'd like you to first grade. Yes, you're going to self-grade. Grade your thinking. What was the first thing you thought about when you saw this? Did you think these 3 thoughts? If you did not think these 3 thoughts, you need to correct your thinking. So there's no way I can measure this for you or tell you. All I'm saying is that when it comes to habits of mind, they only matter when they matter. And when you're taking the derivative, these are the 3 things you want to be thinking about right now. You want to be thinking about basic shortcuts, the product rule, the quotient rule, and the chain rule. Those are the things you want to think about. And that's because you don't have a hint a lot of times. Now you may find as you do practice that your experience leads you to like having a hint. It gives you an idea of what to do. But if we're talking about a truly original problem, which is how the assessments in this class and the AP exam are written, we can't take for granted habits of mind. So we want to think those 3 thoughts anytime we take a derivative. So I bring that up because we don't use the chain rule at all. We use the quotient rule. So if you did not use the chain rule, but you did use the quotient rule. So using the quotient rule, we have the low function, 1 minus sine of x, times the derivative of the high function, the opposite of sine of x, minus the derivative, I'm sorry, not the derivative, that's next, minus the high function cosine of x times the derivative of the low function 0 minus cosine of x. And then we have 1 minus sine of x quantity squared, which please remember is not equal to 1 minus sine squared of x. You get 4 terms from distributing this, and then 2 of those terms combined, so you get 3 terms. Anyway, depending on the calculus you were doing, this right here would be a perfectly acceptable answer. It's also fine if you do a little bit of simplification, which I did none of. Instead, I have a new practice problem for you. This is the function a of b. A of b equals the cosecant of b squared. The derivative of the function a of b equals cosecant of b squared means I need to be thinking about 3 distinct things. I want to think about basic derivative shortcuts. I want to think about the product rule, the quotient rule, and the chain rule. Those are the things I'm thinking about as I'm processing and deciding. So how do I know which to use? Well, product rule, I need to have a product. Quotient rule, I need to have a quotient. Chain rule, I need the chain rule here, don't I? I do. I've got a function b squared inside of another function cosecant. So I need the derivatives of cosecant and b squared. The derivative of cosecant is the opposite of cosecant of b squared times cotangent of b squared, and then I have to multiply by the derivative. Sorry, I have no idea why that happened. Then I have to multiply by the derivative. Okay. There we go. The derivative of b squared, which is 2b. So again, notice how inside we have b squared. Let's try another. This one is going to be L of x. L of x equals 6 cotangent cubed of sine of x. Picking right back up with this delightful problem right here. So some of you I know have already tried it, and that's okay. Some of you have not tried it, and that's okay too. We're going to try it kind of together, kind of apart. So again, that's L of x, which is 6 cotangent cubed of the sine of x. Now, if you're looking at a function and you're just trying to think to yourself, okay, basic derivative shortcuts, product rule, quotient rule, chain rule, how do I know? Well, honestly, the best teacher is not me, it's experience. So that's why you're going to have practice. More on that later. But when you're looking at this, I hope you get in the following habit anytime you have a trig function, which has a power on it. I hope you get into this habit right here. Specifically, the habit of this exponent right here means we're doing the cotangent of the sine of x cubed. I hope you get into that habit. That's going to be a very powerful habit. Okay. Something else you can try to do. If you're looking at one of these and you're like, man, I don't know, is it the product rule? Is it the quotient rule? Is it the chain rule? Is it just a basic derivative shortcut? What do I do? I don't know what to do. Well, something that I will do sometimes and something that I encourage you to do, and again, this is about figuring things out. So we're talking about original problems we've never seen or done before. That's what we're trying to figure out. And I can't possibly do every single type of chain rule problem out there. It's just not going to be feasible. There's not enough time in the world. Well, that's not true. There probably is enough time in the world, but we're not going to spend it on this. We got other things to do. So something I will do when I'm having a hard time figuring out, okay, how do I take this derivative? Do I use the chain rule? Maybe. Do I use the product rule? No. Quotient rule? What am I doing? Is I like to do pretend evaluation. So what do I mean by pretend evaluation? I like to choose an x value, and then I like to pretend evaluate the function at that x value and see what happens. Because what happens gives me an idea of how to take the derivative. So let's say we let x equal 5. What would be the first thing that you do if you let x equal 5? What's the first operation? Well, the first operation is you take the sine of 5, yeah? So you take the sine of 5, okay? So we're not going to worry about what the sine of 5 is, because the sine of 5 radians is some weird number. We're just going to say that it's going to be, I don't know, alpaca. So we don't need to worry about the sine of 5. Okay. So you've done sine of 5. You got your output, which we're just going to call alpaca. What do you do after that? Like, what do you do with alpaca? Well, then you take the cotangent of that, correct? Yeah, we take the cotangent of alpaca. Okay. So the cotangent of alpaca, that's the new thing. And let's say the cotangent of alpaca is H2O. Well, what do you do after you've done the sine of 5 and then the cotangent of alpaca? What do? You do 6 times H2O to the 3rd. And then chemistry flashbacks intensify. So the reason why I like pretend evaluating is not just because I can do made up words. Actually, none of these are made up words. These are all real things. If you don't know that, school is good. Pay attention. But it allows me to figure out how this is working. And I've determined that I'm doing the chain rule here. And I'm doing the chain rule like you have never done the chain rule before, because not only do we have an inside function, friends, neighbors, countrymen, we have an inside function. So you've seen the movie Inception? Maybe, maybe not. I don't want to spoil it for you. A spoiler for Inception. That's Inception. But anyway, we have a thing inside of a thing inside of a thing. We have layers, we have levels, okay? And we know what the inside-most level, the inside man of the inside man is. I'm not being discriminatory, inside man is a term. So, sine, that's the inside, the innermost, correct? Right. So if we go at it in reverse order, you could also come at it from the other way, but I'm doing it this way. So we have the last thing, that is the outermost layer. So that's 6 times, I'm calling it x is being cubed. And I need the derivative of 6x cubed, which is 18x squared, okay? What was the next level? So what did we do before we did all that stuff? We did the cotangent. So the next level is the cotangent. And we need the derivative of cotangent. So inside of the top layer, the outermost layer, was cotangent. The derivative of cotangent is negative cosecant squared of x. And what was inside of the cotangent? That was the first thing we did, the sine. And honestly, the names of all this stuff is completely irrelevant. It doesn't matter what the name is. The concept, though, is significant. The concept is I have 3 levels. That means I have 3 functions I need the derivative of. That's the big takeaway for this one. Now, it's exceptionally hard to put all this back together. So let's practice doing that. So to repeat, we determined that there were multiple levels to the chain rule by doing pretend evaluation. You don't have to do pretend evaluation, but I like it. And we determined that we have this level and this level and this level. So we got to put all these back together. So what are we looking at? Well, we're looking at this. What is this x and this x as well equivalent to? The cotangent of the sine of x. Okay, that's the cotangent of the sine of x. So if you take a look at the derivative I've got down here, we start out L prime, we have 18 times the cotangent of the sine of x squared. That's what we got, okay? So the next derivative is the derivative of cotangent. But what is interesting and unique about this problem compared to the other problems we did, there's a function inside of cotangent. And inside of cotangent is the sine of x. So this x right here, the cotangent of x, that's a sine of x. And this x right here, the opposite of cosecant squared of x, that is also a sine of x. So when I write down the derivative of cotangent of sine of x, I have the opposite of the cosecant squared of sine of x. So we've done another level to the chain rule. And then we finish out didn't work, sorry, by multiplying by that last derivative. And if we had another level, that x wouldn't be an x, it would be something else. And we would keep going until we'd reach the end of all of the derivatives. So sometimes this is called the repeated chain rule. But that is where we will end things for this, our first lesson on the chain rule.